Learn how to apply single variable calculus to real-world engineering problems and become a master problem solver. In this week's Pass the FE Exam episode, you'll learn how to apply calculus concepts to solve a common real-world engineering problem involving single variable calculus, an essential topic from the mathematics and statistics section of the FE exam. This problem was created and solved by mechatronic engineer Shante Thunderspay. Let's jump right in.
In today's question, we are presented with a typical real-world engineering problem. A company needs to design and manufacture an open-top storage container with a total surface area of 48 by 48 square feet. Our objective is to maximize this container's volume while staying within these material constraints. We are provided with 4 possible solutions to this problem. But first, let's take a step back and carefully break down the problem, set up our equations, and solve it step by step. Let's get started. To construct this container, we'll start with the template shown here. Because the container's base needs to be square, our focus narrows to 2 dimensions, the width and the height of the container. By carefully optimizing these values, we can maximize the container's total volume while also staying within our material constraints. Let's use these variables to start setting up our equations. We begin by establishing a formula for the total surface area of our box template. The center square, which forms the base of the box, has an area given by width times width, or W squared. And next, we account for the box's side panels. Since each panel has an area of width times height, and there are 4 of them, their total area contribution will be 4WH. By summing these areas, we arrive at the total surface area equation for the container, given by W squared plus 4WH. Now, shifting our focus to the 3-dimensional box, we can define its volume as the product of its 3 primary dimensions. And since its base is a square, the volume will be given by its width squared multiplied by its height. These 2 equations will form the foundation of our problem and will ultimately allow us to solve for the container's maximum possible volume. To make sure our design stays within the surface area constraint of 48 by 48 square feet, we need to establish a constraint equation that ties our surface area equation to this design parameter. In mathematical terms, the total surface area AS must be less than or equal to the available material. However, since we want to maximize the container's volume, we can assume that all of the material will be used, which means the inequality becomes an equality. Our resulting constraint equation is then given by W squared plus 4WH is equal to 48 times 48. Next, we want to isolate the variable h from this equation, a step that lets us express the container's height solely in terms of its width. To achieve this, we first subtract W squared from both sides of the equation, effectively moving this term to the right-hand side. Then, we divide the entire equation by 4w, the coefficient in front of h. And after this, we arrive at the expression h is equal to 2,304 negative w squared, all divided by 4w. We can now use this expression for h and substitute it into the volume equation we derived earlier. We do this, and then by multiplying in the w squared term, we arrive at a volume equation that depends solely on the container's width w, given as 2,304 times w negative w cubed divided by 4. By expressing the volume solely as a function of width, we simplify our analysis significantly. Instead of juggling both height and width simultaneously, we now have a single variable equation where changes in width directly impact the volume. Now that we've expressed the volume as a function of width, our next step is to determine the width w that maximizes the container's volume. To do this, we need to identify the function's critical points, which are key indicators of where the volume function reaches a local maximum, minimum, or saddle point. Mathematically, critical points occur where the first derivative of the function is either 0 or undefined. These points help us determine whether the volume is increasing, decreasing, or reaching an extreme value. If we visualize the volume function as a curve, these critical points correspond to peaks, valleys, or points where the slope momentarily flattens out. To find the critical points of our volume function, we take its first derivative with respect to the width w, using the classic power rule of differentiation, which you can also find in the FE handbook on page 48 for your reference. We differentiate our equation step by step. After differentiating and setting the equation to 0, the function now has the form 2304 negative 3w squared divided by 4 equals 0. Now, we solve for the container's width or its critical points. First, multiply both sides by 4 to eliminate the fraction. Then, move 2304 to the other side, making it a negative term. Then, divide that whole equation through by the negative 3 term in front of w squared, so it can be isolated on the left-hand side of the equation. We simplify this fraction and take the square root on both sides of the equation, finally giving us a result of either positive or negative 27.71. And since a negative container width doesn't make sense in this context, we discard the negative value, which likely relates to the function's local minimum. This means our final container width is 27.71 feet. In this case, choosing the correct value for the width was intuitive, but this might not always be the case. For example, in problems involving temperature variables, negative results might still have valuable meaning. So, to be thorough, we can mathematically confirm which critical point represents a local maximum and which one doesn't. This is where the second derivative test comes in. The test works by taking the second derivative of the function and substituting the previously obtained critical points into it. If this results in a value less than 0, the function is concave downward at that point, confirming that it's a local maximum. If the result is greater than 0, the function is concave upward, indicating a local minimum. However, if the second derivative equals 0, the test is inconclusive, meaning the critical point could be a maximum, minimum, or an inflection point, requiring further analysis. Let's apply this test. We differentiate the volume function one last time to obtain its second derivative with respect to its width. Using the power rule again, the constant terms disappear, leaving us with a second derivative equal to negative 6w. Now, substituting our critical values into this equation, we find that for w equal negative 27.71, the second derivative is positive, meaning this point represents a local minimum. On the other hand, for the positive critical point, the second derivative is negative, confirming that this point is a local maximum. Now that we've mathematically validated this result, we can confidently move forward to calculate the maximum possible volume of our container. We use the volume equation derived earlier, where the container's volume is expressed in terms of its width. By substituting the critical value into this equation, we calculate the maximum possible volume of the container. After performing the necessary calculations, we find that the container can reach a maximum volume of 10,641.72 cubic feet. If you're short on time during the test, this is the point where you should verify your answer by checking the multiple choice options. But if you want to validate that the container meets the material constraints, here's what you can do. First, we refer back to the formula we derived at the start of the problem, where we isolated h in terms of the other variables. Substituting the optimal width we found, we determined that the required container height is 13.86 feet. Next, we substitute this height and width back into the original surface area equation. Calculating this, we confirm that the total surface area is 2,304 square feet. And when we take the square root of this value, we find that it matches our original target surface area of 48 by 48 square feet, confirming that our calculations were correct. We can now confidently move on, knowing that the volume we found is accurate. And that wraps up our problem. The correct answer is A. Always take a moment to carefully review all the options before making your final decision. To conclude, the objective of this problem was to optimize a container's volume while ensuring it adhered to a given surface area constraint. Throughout this process, we derived mathematical expressions for both surface area and volume, allowing us to establish a constraints equation that defined their relationship. By expressing volume as a function of width alone, we simplified our calculations and applied both the first and second derivative tests to determine the container's optimal dimensions. By systematically applying calculus and optimization techniques, we successfully determined the maximum volume of our container while staying within the given surface area constraints.
I hope you found this week's video helpful. In upcoming videos, we will answer more of your FE exam questions and run through more practice problems. Pass the FE exam will publish videos weekly, so please be sure to click that subscribe button as you'll get expert tips and tricks, including practice problem solutions weekly to ensure that you pass the FE exam. And please, I encourage you to ask questions in the comments below. I will read and respond to them in future videos. Maybe there's a specific topic that you might be struggling with, or a question that you need answered. Pass the FE exam will have you covered. I'll see you next week on Pass the FE exam.